Morning, everyone. So today we're going to continue on with our energetics chapter here. Up to this point here, we've been focusing on a guy called delta H, the enthalpy change of the reaction, whether we're endo, whether we're exo. I told you here the better part of this chapter here is finding 7 different ways of finding this delta H. I'm going to give you a summary chart later on that summarizes the formulas along with where you can actually find the data here on the data booklet. I just want to emphasize those 5 ways that we did so far. Let me just repeat them here. The delta H here, I could find it using calorimetry. I could find it using bond enthalpy. I could find it using Hess's law with those mini equations. I could use formation numbers. I could use combustion numbers. Those are 5 perfectly good ways depending on sort of what data that we have. Those are all different ways so that I can find the delta H. We're going to find, however, if I look at the worksheets and look at the practice problems here, up to this point, those have mainly been looking at covalent compounds. So today and tomorrow's lesson here, we're going to switch over to actually looking at ionic compounds, and this is going to end up forming our method number 6 and 7. In case I have an ionic compound, in case I have a lattice structure here, how could I also get at the enthalpy change of the ionic compound? So if you can keep that in the back of your mind here, today's lesson on Born-Haber is going to be method number 6. This is going to be focused on ionic compounds. And how these lessons here are structured here is we're going to have one big equation that we're interested in. There's some enthalpy change, in this case here for an ionic compound here. As a lattice, we end up forming, let's say, positives surround themselves with as many negatives as around. Because I know ionic compounds end up forming this, what I'm interested in is how much energy do I need to put in to completely rip the structure apart. Now, I know ionic compounds typically are solids at room temperature, which means their melting points are very high. Not only are ionic attractions fairly strong, there's a ton of them I need to break. I would expect that this lattice enthalpy should be a fairly endothermic number to rip this guy apart. So what we're going to do is we're going to introduce one delta H that's special to the ionic compound. And then what we're going to do is we're going to try to apply Hess's law. Hess's law says as long as I get from the same start to the same finish, it doesn't matter the pathway I take, the overall delta H of the detour will end up adding up to the delta H of the overall equation. So without further ado, let's take a look. Born-Haber cycle here, the big equation that I'm going to introduce for you, again, here's another definition for you. We're going to talk about something called the lattice enthalpy. The name is actually fairly good. It is the enthalpy of the lattice. It is the enthalpy change or the energy change. There's that pesky little 1 mole again. I want everything's quoted for 1. So in case later on I can scale it up times 2, times 5, whatever I want. We are focusing on ionic compounds. And basically what I'm doing is I'm completely ripping this guy here apart. As I rip this guy here apart, I don't want to see any positive close to any negative. So because this one here as ionic compound typically is a solid, I probably want to separate them enough. Maybe I want to put them in the gas state. I want them to be so far apart that there's no semblance of any lattice, nobody's connected anymore. So it's going to be broken apart into the constituent, the ions that make it up. Notice that the ions were always there. It's just that in the ionic compound we had balanced out our formula ratio so that they canceled out. As I just rip apart these ionic bonds and I separate cation and anion, they're just already having the charge and I just want to put them into the gas state. So in general here, we're going to do the endothermic convention. Some textbooks actually do it the opposite way. But we're going to define lattice enthalpy as starting from the lattice, starting from the ionic compound. It's solid, happy the way it is. I forcefully come in and put in energy, and I completely rip this guy here apart. I want to separate the positive from the negative. The delta H here is going to be endo when I do that. We still have a standard condition here. I listed for you the standard state, 25 degrees. We have 1 bar of pressure. If I have solution, it's going to be 1 molar. We'll see that more tomorrow. Stable allotrope, all that. Sometimes I just mentioned lattice enthalpy is given to you as going the opposite way. So lattice enthalpy could be going from the gases back to the solid, but nonetheless here positive is endo. We're going to rip this guy here apart. I need to put in energy or this lattice had no reason to separate. Here's the kicker. Experimental lattice enthalpies cannot be measured directly. It's too hard to do calorimetry on this. You can imagine here trying to supply heat. It needs to be evenly distributed through the whole compound. It needs to rip apart all the bonds in almost like an instantaneous fashion. I want it to hit some maximum temperature change. I don't want it to be equilibrated room temperature. I also need to, even if I manage to separate this compound, I also need to supply the heat energy good enough that this can actually liquefy the metal and then become a gas. Same thing with the non-metal, it has to become a gas. There's way too many steps that are involved, which is why it's hard to do experimentally. However, what we're going to do is we're going to actually create something called the Born-Haber cycle. we're going to create a bunch of little mini steps, hypothetical, sure, but by adding up all those mini steps, as long as I have the same start and the same finish, I'm going to end up getting the same overall delta H change. So Hess's law here is used on a series of reactions, and what's upcoming here is I'm going to show you some of those mini equations that we're going to have to use. So Born-Haber cycle here, whether the question asks you sketch a Born-Haber cycle or not, I would just draw it anyways. It's easy enough, and it makes sure that you have the signs correct. So Born-Haber cycle is an enthalpy level diagram. It's like having an enthalpy cycle, and it represents the formation of an ionic compound. It represents the making of an ionic compound, but it represents it as a bunch of simpler steps, elementary processes, and if I add up all those steps here, I'm going to get the overall. They're going to simplify things a little bit here. You don't need this in the definition, but they are going to just specifically look at alkalis and alkaline earth metals, group 1 and group 2, and they're specifically only going to look at oxides and chlorides. They could have looked at other ionic compounds here, but we get other problems with some of those later on. So let's have a look at, we know what lattice enthalpy is. We know basically what we want to do is we want to rip this guy here apart. In starting off drawing this Born-Haber cycle here, I'd always format it in the same way so you get some familiarity. Let's imagine I try to do NaCl, so just table salt. It's an ionic compound. I'm going to imagine to lattice this guy. If I supply the lattice enthalpy, the delta H lattice, I assume that the cations and the anions would be completely ripped apart. They were in the solid state here, and now they're going to be gases, and I'm going to assume that that's a very endothermic reaction. I need to forcefully come in and I need to rip this guy here all apart. To start off this sort of enthalpy level diagram, here's sort of the cycle that we're going to end up with. I typically put the solid down here. We'll see the reason a little bit later. So enthalpy solid. I'm going to draw an arrow upwards, and I'm going to say, well, I want to make the Na plus as a gas, and I want to make the Cl minus as a gas. I'm going to start off with that big equation. This guy here is the new guy we call delta H lattice. That's the one that experimentally is really hard to do. It's really hard to transfer all that energy all at once. What I'm going to do is I'm going to engineer a bunch of mini steps here. The first step here I actually didn't include for you because we just did a formation equation. First thing I want to do is I want to separate sodium and chlorine. What if I just started off with the pure elements? So just plain old sodium, plain old chlorine the way that they normally show up. Let's make 1 mole of NaCl, since lattice enthalpy later on will rip apart 1 mole. That means this can be a 1, this one here would be a half. But let's use not only the pure elements, these are in the regular states. So sodium is a solid, chlorine is diatomic, it's gas. You should be able to tell me that this one here is a formation equation. So that at least tackles one of the issues here. Our ionic compound has cation and anion together. By undoing the formation arrow, formation is going from left to right, but if I go right to left, I end up negating the formation, right? Undoing the sign, and I end up separating positive from negative. Now that I have the metal and the non-metal separate, I can go back to chapter 3. I can, one step before that. There is one new mini equation here, which is called atomization. I'll do step number 3 for you first. Atomization by definition, again, in the definition, there's this pesky little 1 mole. I want all the values are quoted for 1, so therefore I can actually scale it up later on if I want. Atomization is always defined as making 1 mole of the gas atom, right? That's why it's called atomization. You're making an atom of something, formed from the elemental, the regular state that it comes in. So for example here, we have sodium right now. The normal state here is solid. If I want to atomize this, it would end up making 1 mole of gaseous sodium. So there's that 1 mole. This enthalpy change here is called enthalpy of atomization. That's atomization for sodium, so I can specify here this is for sodium or for the metal. For the non-metal, it's actually a little easier because chlorine here is actually already a gas. It's not atomized though. Chlorine, unfortunately, is still diatomic. It's still Cl bonded to Cl. If I atomize it, I end up one-way arrow. I want to make 1 mole of this element in the gas state. This one here would actually be a chloride radical. It would be unstable. But this one here would actually be the atomization of chlorine. So atomization is the new step that we don't see. This one here is not on any table, not on data booklet. So either they give you this problem, or in a later question, they can actually give you all the other values and actually ask you for the atomization value. So that's a new one here. We want to produce 1 mole from the sort of our regular exposure of them, the regular sodium, the regular chlorine. It's important to atomize first, then we can go back to chapter 3 here. Now that we're at the gas state, metals tend to want to get ionized. We tend to want to lose that electron. We tend to want to pick up a positive charge. Remember ionization, this time we're not going to just focus on, it had to be quoted for 1 mole. There's also a little pesky little it has to be 1 mole, it has to be gas, like we mentioned. So I wouldn't be actually ionizing from the solid state first. I have to atomize, I have to put it in the gas state. Once it's in the gas state, then my ionization energy term makes sense. I want to ionize the metal from the gas to the gas ion. That's the one that was endothermic, right? I need to forcefully come in with a pair of tweezers, and I want to remove this electron. We had talked about in chapter 3, successive ionization. If I had to come back again and pull off another charge here, it generally gets harder and harder. So, ionize for the metal. We actually want to electron affinity for the nonmetal. Electron affinity involves, well, chlorine is unstable because it says radical here. Let's take an electron from infinity and let's pretend to add that electron. Let's give it that electron. What is the electron affinity? What's your enthalpy change when you go from chlorine gas radical to Cl minus, chloride as an anion? That's going to be the electron affinity. So here's a generalization here. Although you could do ionize for the metal or the nonmetal, in this Born-Haber cycle, ionize typically is better for the metal. Because the nonmetal typically is going to get a negative charge here, we're going to actually electron affinity the nonmetal. Both of them involve this 1 mole, and both of them have to be gas, so it involves that we had to have atomized it first. And here, before we go through a little more details here, this is what Hess's law says. Hess's law wanted to do the strength of the lattice. It wanted to figure out if I could experimentally rip apart this lattice. I want to figure out how strong this ionic compound is. I'm going to start inputting energy if I want to completely separate them, and I want to completely go from Na to Cl minus. What I can do here is I can work around this side of the cycle. I can undo the formation. I can follow the atomization, follow the ionization electron affinity. I'm going to end up getting to the same position. Hess's law says, great. It doesn't matter the detour or the straightaway pathway. The combination of all these mini steps here ends up giving you the overall. So I know that looks a little bit scary, but that there is our Born-Haber cycle. It does end up arising as a formula. So if you like formulas, you can memorize it, but I find it's generally easy enough to do Hess's law. And so far, I've listed the formula for you down here. This is a slightly simplified formula. But if you look down here, it says your lattice enthalpy. It says this one here in the red. Your lattice enthalpy starts from the ionic compound and ends up there. Well, what we could do is we can flip the formation arrow. Formation makes this compound here. If I undo it, I'm going to pick up a negative sign. For the metal, I'm going to atomize and then ionize. So put it in the gas state and then charge it. For the non-metal, I'm going to break up the bond here, atomize it, get 1 mole of it, get that radical, and the electron affinity, give it that electron that it wants. Those would be the detour steps around, and the combination of all those steps here would give you this lattice enthalpy overall. Many questions do ask you just calculate lattice enthalpy, but just like you might expect here, I might give you the lattice enthalpy. I might make one of these other ones the unknown. Normally atomization can be unknown. I can basically have, we'll do that problem later on, but I can basically have sort of, if I want to start here, I want to end here, I can work my way the other way around the table and get whatever the missing link is. I can always just have one unknown in this expression. Now a couple little pointers here as we go through a few examples. Why did I draw the cycle like this? Why did I draw the solid on the right? Not only does it give us a nice sort of systematic way of approaching these questions, this diagram here, they actually show you to use sort of more generically here. You can see if you can follow along. This diagram here is roughly on an energy level diagram. So the higher I am up on this cycle here, I would expect higher energy. And remember, in general, things that have more energy have more capacity to work. There's more that can go wrong. We're actually at a more unstable state. You have to endothermically put in energy to go up. So for example, if I took the metal was happy. But if I atomize it, if I want to put it in the gas state, all I need to do is heat it. I need to melt it. I need to make it in the gas state. I'm putting in energy, endothermic, my energy goes up. Ionize, I come in with a pair of tweezers, I forcefully remove it. Again, endothermic. Those ones, no surprise, I'm actually endothermically, I'm getting to a sort of more higher energy state, a more unstable state. Similarly, for this chlorine here, chlorine is actually a little bit special. Even though this diatomic here, even though it already is in the gas state, sorry, I just noticed I made a mistake here. This one here should actually be chlorine as gas. So in this case here, what we've actually done is chlorine already started off like this. My atomization equation has, I want to make 1 mole of chlorine gas from the way that it normally appears, which is chlorine gas like that, but I'm going to need to pick up a factor of half like that. In this bottom equation here, this is called atomization, the making of 1 mole of your nonmetal from the way that it normally appears. If you look chemically speaking, what I've done is I've actually taken a Cl and a Cl, All I've done is I've actually homolytically separated these two. I put in the energy to rip these two apart, so that explains why atomization is actually endo for the non-metal as well. But all I'm actually doing is I'm actually breaking the bond. Was there another way we actually trace breaking bonds in an earlier lesson? Hopefully you were able to say to me, bond enthalpy. If you bond enthalpy something, if it's in the gas state already, I'm forcibly ripping apart the bond, and we end up getting 2 chlorines. So what we're seeing is for diatomic compounds, the atomization equation is exactly going to be half the bond enthalpy. So therefore, even though atomization is not on the data booklet anyways, you can sometimes, especially if we're dealing with halogens, especially with this simplification, we're looking at oxides and chlorides, which are diatomic, and they are gases, you can approximate the atomization as roughly half the bond enthalpy. And that's because the atomization is the sort of divide 2 form of the bond enthalpy equation. This works fine for chlorine, this works fine for fluorine. If later on the next question is coming up, it's going to be on iodine. It does not work for iodine, it does not work for bromine. It's not the problem that iodine and bromine are not diatomics. Bromine is diatomic, iodine is diatomic. You do involve breaking these bonds here, but if you remember in the regular conditions, bromine is actually a liquid, iodine is actually a solid, and that's something that bond enthalpy can't do. Bond enthalpy has to be for gas. So just watch out for that here. Sometimes you just need to approximate. If they give you atomization, by all means just use it. But if you have to approximate it, if it is a diatomic, roughly half the bond enthalpy is the atomization. All of those are endothermic. They really like asking in paper 1, which of these mini steps here, they may give you some like sodium becomes sodium gas or chlorine becomes Cl-, which of these has a different sign than the other ones. The only mini step that was actually exo, the one that is sort of misleading here, I still drew this arrow upwards, but just keep in mind here, if I have a chlorine as a radical, that's super unstable. If the electron actually passes from the metal and the electron gets added to the chlorine, it puts chlorine in its more stable Cl- state here. That's the only energy change that's exo, which is why in the proper diagram here, it actually brings it back downwards. It's just a little more confusing when I try to draw the circle here. It has most of them right. Most of them is sort of going up means endo. Just keep in mind here, this arrow here is actually going to be exo. The electron affinity is actually putting the chlorine going from the radical to the noble gas state here actually puts it more stable. So that's what it takes to be a Born-Haber cycle. Born-Haber cycle, as we step through 2 examples here, Born-Haber cycle does sort of indirectly measure the strength of the lattice. Because an ionic bond here is a Coulomb attraction, F is kq over r squared, what I would imagine here is if I have higher charges, that could be, so higher charges, that could be having more protons. If I'm looking at an element that has more protons, or it could be higher oxidation state. So higher oxidation state. So if it was like sodium +1 to magnesium +2, right? The bigger the charges, I would expect the stronger the force. Similarly for radius here, radius, because it's on the bottom, I want smaller radius. Usually when you have more protons, it means higher Z effective. It means the thing is tinier anyways. The tinier the radius, I would expect the ionic compound to, ionic bonds to be stronger as well. So the electrostatic attractions are exactly the same as we saw in chapter 3. It is stronger with higher charge, smaller radius. However, this is just an experiment to note. If you had to pick just one, if you had to decide, is charge going to have a bigger impact or radius have a bigger impact, we would say charge has a bigger impact. Going from +1 to +2 is a more dominant change than, say, a radius dramatically changing size. And we can actually rationalize that using the next example here. I've given you lattice enthalpies. You can actually find lattice enthalpies on table 18. We'll pull that out on tomorrow's lesson. Let's start off with NaCl, and let's sort of roughly match out where they are on the periodic table. Na is right here. Cl is right here. They give you the theoretical value for NaCl. The lattice is 769 strong. If you want to do this process and completely rip apart the NaCl, assuming you've done all this Born-Haber stuff here and you ripped it apart to become gas ions, you need to put in 769. What if I compare it to the elements that are exactly 1 row lower than it? So what if I increase the radius from NaCl? Let's make NaK, so K is right below it, Br is right below it as well. All that's happened is I'm 1 row lower. Sure, I have more protons, but if you look at the Z effective, the Z effective is still roughly K is still +1. This one here is still +7. Everything is identical except my radius has changed. Even though my radius has changed, I'm one shell bigger on both cases here. You'll notice that the lattice enthalpy for this new compound hasn't dropped by much. It's only dropped by almost less than 100 there. However, if I go from sodium chloride to magnesium oxide, so again, rough placement on the periodic table, magnesium is right beside sodium, so size-wise it's roughly the same. I couldn't find the value to be fair, but I'm going to put Mg with oxygen. Oxygen is actually a tinier size there. We already concluded that the radius itself doesn't make such a dramatic impact. The more important impact here is going from sodium. Sodium is Na+, and whereas Mg here is actually Mg plus 2, Cl used to be -1 or bromine -1, now oxygen is -2. Going to that higher oxidation state, you'll notice a dramatic increase in the ionic attraction, a dramatic increase in the strength of the ionic bond. So yes, although both features, the charges and the radius, have some impact, have some say on the ionic attraction, if you have to only pick one, experimentally, charges are more important. So let's just work through two last examples here. This question here, a little bit of a cheat because, like I said, they're only going to give you alkalis and alkalines, oxides and chlorides. I threw in silver iodide for you. So silver iodide is the compound AgI. Even if they didn't ask me construct the Born-Haber cycle, that's where I would start first. Here's how I would begin here. Start off with the solid here on the lower right-hand corner. Start off with the formation, just going across. Silver iodide is made out of silver and made out of iodine. That one there is so far called formation. For formation, not only am I starting from the elements, it's the elements in their standard state, in their regular state. So metal here tends to be solid. I already did I2 as a diatomic. This one here is going to actually be solid, so be it. For it to actually be a formation, I'm stuck with a pesky little 1 here. So therefore, I might have the odd fraction. In the next example, we actually will do like MgCl2, which actually needs 2 chlorines. I can just leave that as a Cl2 like that. So that so far is the formation. That's just sort of separating the metal and non-metal. I know that's going to be one of my mini steps. Normally, you would find formation values on table number 12. However, like I mentioned, table number 12 typically is all covalent compounds. It's typically not going to give you the values that I want for an ionic compound. So we have that one there. I'm going to start off with the big equation here also. If I lattice this guy, if I put in the energy to completely rip this guy here apart, I'd imagine getting silver. It's only has a +1 charge, it's gas. The I minus also has a gas, -1 charge. That would be involved in lattice, that would be involved in ripping this guy here apart, and that's the endothermic convention going from solid to gaseous. Now what I'm going to do is I'm going to slowly watch what has to happen to the metal. The metal first has to be atomized to become Ag gas, right? Making 1 mole of gas is called atomization. I need it to be gas first, then I can ionize the metal. For the non-metal, similarly here, this time I can't do that approximation of bond enthalpy because bond enthalpy needs it to be gas. For a solid, they better give me the atomization value. Atomization would make 1 mole of I, that's perfect. Half an I2 does make 1 mole of I, that balances off. This is now making 1 mole of gas, and then I electron affinity, although we know electron affinity is actually exothermic. That's the one that actually puts me more stable. It allows the radical to pair up. In this case here, they are interested in calculating the lattice enthalpy. So Hess's law says, I'm interested in going from here to here. That's my start, that's my finish. What I can do is I can go this way around the cycle. So let me just write that out as a formula here. The delta H of the lattice, that's the one that I want. That's the one that I've highlighted in green. Right? So to get from that start to that finish, what I would do is I would have to flip the formation arrow, minus the formation. For the metal, I need to enthalpy of atomization of the metal, in this case here it's Ag, plus the ionization of Ag. And then for the non-metal here, I'm going to atomize the I, and then I'm going to electron affinity. I want to give it that electron, also the I. It has to already be in the gas state. So that would mean here I better have all these numbers here. You'll notice in these questions, if they're not on the data booklet, they actually give you a lot in the question. So in this case here, it says, no, the formation enthalpy of an ionic compound is -63. So let's just punch our way through here. Negative of -63 plus atomization values are not given on any table. So you notice they have to give it to me in this question. The atomization of silver and iodine are this and this respectively. Means silver is the first number. So silver is going to be 285. That bottom number here, atomization iodine, likewise is going to be 107. And then what I need is I need the ionization of silver, and I need the electron affinity for iodine. Where might I get those? Hopefully you remember from table 8. Back in chapter 3 here, when we actually looked at the periodic trends, remember we had a periodic table sort of schematic, and we would just look in the sort of appropriate corner for that particular element. How hard is it to pull off the electron on silver? Just pulled up my table here. Silver's ionization, double check my numbers, I'm getting 731. Whereas for electron affinity for iodine, I'm getting negative 295. And we verified here, majority of these here are actually endo. They put us in a more energetic state. There was no reason to become a gas or lose electrons. The only one that was exo is the electron affinity. So let's just crunch our way through. The math ends up fairly simple. We're just doing simple pluses and minus. Take 63, add 285, 731, 107 minus a 295, and I get 891. The units are going to be kilojoules per mole. Our whole data booklet has values, enthalpies, and kilojoules per mole. What does it mean if delta H here is positive? This one here would then therefore mean endothermic, and that should match up. Because this lattice is so strongly held together, you need to input in an extra 891 to completely rip it apart. Sometimes very sneaky, they try to ask this question backwards. They try to say, let's say multiple choice, which one of these reactions here is most exothermic? What I can do, because I found AgI becoming the gaseous ions is positive 891, what if I did write Ag plus and I minus, these are gas, and then forming AgI solid? This one here would therefore be delta H negative 891. Right? Let's compare it to the NaCl we did earlier. NaCl, the positive convention going from the solid to the gases was 769. What if I said it in reverse? What if I said Na plus as a gas and Cl minus as a gas, and it becomes NaCl? I'm basically undoing lattice enthalpy, and now this one here is going to be the negative 769 that we said earlier. So you see, not only lattice enthalpy is a measure of the strength of the ionic bond, if this one here, in this case here, because AgI is a stronger ionic compound, it's more endothermic to rip it apart, but it also is more exothermic. When I end up forming that bond, when I end up creating the lattice, I end up releasing more energy than something that isn't as good, isn't as strongly held together. Not by too much here, it's negative 891, negative 769. We still use the endothermic convention from solid to gaseous, but sometimes they ask this question backwards. One last little note here, the reason why they typically only give you alkalis and alkalines. This one here, there's a little bit of an assumption going into this with the Born-Haber. It's not a problem with Hess's law, same start, same finish, that's all good. But what they can do is they can compare it to another theoretical model. If I assume a real perfect ionic compound, if I assume that silver as an ion and iodine as an ion, if I really could do a KQQ over R squared to find the force of attraction, I would be assuming this is 100% ionic. I would be assuming that there's no overlap at all. The electron just got transferred, and I can just measure here. Oh, I know it's plus 1, I know it's plus 1, I know the protons you have, I know the radii that you have, and whatnot. That's going to be a perfect ionic compound. It assumes, this theory of ionic compounds, it assumes it's perfectly spherical, it assumes that it's all perfectly electrostatic, it assumes that there's no overlap at all. In that case there, the theoretical value for AgI is actually 881. Let's compare it to the 891 that we got earlier. First thing, it's close, right? That's good to see, right? I want to make sure it's consistent. But what we're going to see here is any discrepancies, anytime there's any differences between what your Born-Haber says and what this new theoretical ionic model, a perfect KQ/R squared kind of model says, any discrepancy, you would just make a note. It's due to the covalent nature of the bond. Even though AgI does transfer the electrons, even though it is supposedly going to be an ionic bond, if you look at where Ag is placed, Ag is actually a much tinier radius, right? It's not going to lose to the non-metal as badly. It's actually going to pick up some of that covalent nature. Remember, we're not never going to be like 100% ionic. We're going to be somewhere along the spectrum. Sure, AgI might so far still be ionic, but it might pick up some covalent nature, and it's that covalent nature that the Born-Haber cycle picks up. That does become a slight assumption here. If you have another way of finding delta H here, maybe that way is better. But so far, it's just telling you here, those additional contributions from the covalent nature, the electronegativity difference is a little bit smaller. It's not as ionic. It's not as big as that 1.8 from before. And therefore, if you actually check out the numbers here, accounts for higher than expected lattice enthalpies for silver. That's just the size of it, 892. Sodium, that's the size of it, and 705. If you actually look at their just the individual, anytime there's any discrepancies, anytime there's any differences, you can just say covalent nature. So they try to avoid this fact here by just quoting for you, oh, we're just going to use alkalis and alkaline earth metals. Those ones are going to be the more ionic ones, and that's a case where that's the case where your Born-Haber cycle should be a better approximation. Lastly here, let's do one last example. There's going to be a worksheet that gives you some more practice with this one here. We're going to do a question. What I want you to find for this question, it's actually question 2 on the upcoming worksheet. I want you to find for me here, calculate the atomization enthalpy of magnesium in the compound MgCl2. Right? So I'm interested in one sort of mini step. They have to give you a bunch of values here. I'm going to give you the formation enthalpy. Right. Normally formation enthalpies, like I mentioned, is on table number 12, but because it's ionic here, formation enthalpy is negative 641. That's kilojoules per mole. I'm going to give you the second ionization energy, because magnesium actually needs to be ionized twice. I only have the first ionization on table 8. So second ionization is some 1451. Also going to be endothermic here. Let's see if I need to give you any other one. And let me give you, actually you can look up the lattice enthalpy. Those should be the only two. Let's have a look. So although they didn't say construct the Born-Haber cycle, I would actually start off that way. I would start off, I'll draw a nice and big diagram here. I'm going to start off with the solid on the lower right corner, just always consistently. So MgCl2, this is a solid. I'm going to start off thinking about latticing it. When I lattice it, I put in the energy and rip this apart to form the gas ions. I have Mg plus 2 gas, and I have Cl minus gas. My mole ratio here says if I rip apart 1 mole, I do end up with 1 and 2. So that, so far in the blue, I'm going to color code this here, that's the lattice enthalpy. I'll show you on a table later on how you can find that number. First step here is to separate the positive from the negative. So let's start off. Magnesium is usually a solid. Chlorine is usually diatomic as a gas. Notice this time, it actually needs both chlorines. So this time, the mole ratio is perfect. So this one here is just the heat of formation. That's the value I gave you here, negative 641. What's going to happen here is, let's look at the metal first. The metal so far is in the solid state here. I want to do metal in the gas state. So that's the atomization for the metal. Once it's in the gas state, I can first ionize. When you first ionize, it becomes Mg plus 1, and then I can second ionize. Remember, ionizing, although it does increasingly get harder, it is only for 1 electron at a time. For the non-metal, similarly what I want to do is I want to atomize it. I want to make it Cl, like 2Cl like that. So I want to have 2 chlorine radicals. I know it's less stable. That's actually going to be, if I had atomization, it would have to be twice the atomization value. Atomization would have made only 1 mole of Cl, because I want to actually break up both and actually keep both. It's going to be twice the atomization. And in a similar fashion, now that the Cl is a radical and it's a gas, I get an electron affinity. Electron affinity was per mole. That's why in that pesky little per mole, it saves us here. Because I need to do that twice, I'm just going to double the value for Ea twice. So that's what we're used to. You can use the formula. You can just go lattice enthalpy is the flip of formation and flip of all these, and you can just do some algebra. I just want to show you the power of the cycle here is you can start anywhere you want. In this case here, I want atomization enthalpy of magnesium. I actually want to start from this guy, and I want to get here. Remember, atomization is something that you don't have. What you can do here is Hess's law. Hess's law says same start, same finish. If you can't do that step, if that's not in any data booklet, you can actually loop this way around. So in that case there, by doing the cycle in this fashion, you actually have done a little bit of the algebra. It's not wrong if you did lattice enthalpy minus formation and did some algebra that way, you'll still get the same answer. So let's see what we get out of this cycle here. Hopefully I have all the numbers I need. If you want the atomization of magnesium, if you want to start here and end here, what I'm going to want you to do is I want you to follow the formation arrow. So this time you're going to just take the formation arrow as is, so don't flip the sign. You're going to follow the lattice enthalpy arrow. Right, that takes you from the lattice to the gaseous ions. You're going to undo the ionizations. So you're going to undo minus the second ionization for magnesium minus the first ionization for magnesium. Right, I want to get exactly the same match. I want to get rid of it being charged. I want it just to be gas magnesium. And unfortunately, because sort of magnesium wasn't by itself here, I would also need to undo the chlorine parts. So I would need to actually minus off twice the electron affinity. I should always say it's the enthalpy change of electron affinity for chlorine. And I want to minus off twice the atomization of chlorine. So that's what I can read from the cycle. So even though they didn't ask me draw the Born-Haber cycle, I want to draw the cycle so I know which ones I'm adding or subtracting. The math is still super simple. It's still just simple pluses and minus. It's just a matter of looking through all these numbers here. So let me just hint at these numbers and I'll let you solve your way through here. Formation number here, this is negative 641 that was given to you. The lattice enthalpy, you can try looking on table number 18. I believe it's there. I will take another look at tomorrow's lesson. Second ionization I was given in the problem, so I'm going to minus off 1451. First ionization as well as electron affinity, I can look at table 8. So lots of using your data book in this valley. The one that I told you was not on any table, this one was atomization. What I'm doing here, when I atomize, I end up making 1 mole of Cl from half of Cl2. It was gas and gas. We're going to backtrack and we're going to say, well, all we're actually doing is we're actually just ripping this guy here apart. So if I did instead Cl2 gas and actually makes 2 gas like that, this one here would be called bond enthalpy, whereas this one here is called atomization. So earlier I had said atomization is roughly half the bond enthalpy. This time I really do want to have 1 full Cl2 become 2 Cl radical. I can approximate this twice atomization. I can approximate it with the bond enthalpy on table number 11. All right. So hopefully you have all the values there. Let me just double check for you so that you can finish off this question. If you look up table 18, we're going to use it a little more detail tomorrow. You should find that, yes, the lattice enthalpy for MgCl2, and you can find, therefore, the missing link here is the atomization. So have another look through the table. Make sure you're comfortable reading the values on different tables there. If you have any questions, let me know. Thanks, guys.